So let's take a quick look at the theories and mechanisms for the extratropical forcing of the tropics. So we've looked at the evidence for the existence of such forcing for the boreal winter and summer months already. Here we just touch on what kind of theories have evolved over time, what kind of models have been used, and observations, and so on. Just a brief introduction here. This is from chapter 3 of Peter Webster's book on dynamics of tropical atmosphere and oceans. You can look up the course on my YouTube channel for the details. The background is that Jules Charny in the 1960s actually started to think about the extratropical forcing of the tropics from a very different point of view, which we will see here. So the idea is that when you have this is the cross section of zonally averaged isopycnals, which are constant density surfaces, plotted against pressure for the northern hemisphere winter for 1998 to 2010. So December to February. DJF is typically the boreal winter months. In the mid-latitudes, the vicinity of the westerly maximum, the atmosphere is highly baroclinic, so the angle between gradient of pressure and gradient density is high. Whereas when you come into the tropics, obviously they are parallel to each other, which means the grad P cross grad rho is 0, which is the definition of a barotropic system. So density in this case is just a function of pressure. So you can see that in the tropics the gradients are almost parallel, indicating a lack of baroclinicity, which raises questions about how the lower atmosphere communicates with the upper atmosphere when there is no convection. So convection can produce strong vertical velocities, but how do you trigger convection in a system that's so strongly barotropic? Because in a barotropic system you cannot convert available potential energy into kinetic energy of so the P of the background state cannot be connected. So Charny was coming at it from a scaling argument. So looking at the extratropical scaling of the horizontal scales of 10 to the 6 meters, Coriolis of 10 to the minus 4 per second with a background velocity of 10 meter per second, so westerlies, and Rossby number being very small, so you know what that means, the inertial versus planetary vorticity or acceleration terms. So there you can have a strongly divergent system with a very strong communication between the lower level and upper level. So we are looking here at the vertical dimension. In the tropics, if you use the same scaling of 10 to the 6 meter and the appropriate Coriolis and the dimensionality of the zonal winds, the Rossby number is close to 1, so you end up with a non-divergent system with upper level easterlies and lower level westerlies. So this is the schematic representation of the degree of vertical coupling for dynamic modes of different scales in the tropics and extratropics. In the extratropics with length scale of 10 to the 6 meter, tropics with the length scale of 10 to the 6 meter, and tropics with 10 to the 7 meter scale. The vertical arrows denote vertical velocity and the degree of communication between the lower and upper troposphere in the divergence. So when you increase the scale to 10 to the 7 meters, then for the same background velocity you can produce strong divergent flows and increase the communication between the lower level and the upper level. So Charny thought this was a conundrum, so he had a hypothesis. The picture of the tropical circulation that emerges is quite different from that of the conventional Hadley circulation. The rising motion is much more concentrated in a narrow band and does not necessarily occur at the equator. We know that the ITCZ is off the equator. The subsiding velocities are small and spread over a larger area, so you have ITCZ, which is very narrow, and the rest of the subsiding branch of the Hadley cell is very broad. And the circulation is not necessarily symmetric. We know that. If the ITCZ is not on the equator, then the circulation obviously is not symmetric. You have strong cross-equatorial flows. The quasi-non-divergent source-free flow acts to transfer lateral influence from the extratropical circulation to the intertropical convergence zone, so that the position of this zone is determined by the extratropical circulation in both hemispheres. So this is a dramatically different idea than a thermally direct cell that we invoke in the Hadley circulation. In the conventional Hadley circulation, we always say there is excess energy in the tropics, air rises, there is convection, and then there is divergence and the Hadley cell. All right. So the ideas that have evolved since obviously have tried to close this loop, and the ideas of extratropical forcing of the tropics evolved from those, and this paper of Chidong Zhang, which is a follow-up to the Zhang and Webster paper, looks at laterally forced equatorial perturbations in a linear model with mobile forcing. So I'm just using this as one example of how the theories and mechanisms for the explanation of extratropical forcing of the tropics have evolved. There are many, many, many more papers that have arrived later on by various people. So this linear model basically looks at a two-dimensional model mean zonal flow. It has westerlies and easterlies, and there is a westerly duct provided to emulate the real world situation of the westerly duct we have been looking at. And the lateral forcing is provided by picking this wave forcing with a zonal wave number of 4. So the end-to-end you should have 4 troughs and 4 ridges, which is what you see here. The contours denote forcing amplitudes that are 40% and 80% of the peak, and negative values are plotted with dashed contours. So you are just providing this wave forcing as if you are tying the rope at one end and moving the other end up and down to see the wave motion. So in this case, the idea is to look for relative amplitude of forced equatorial waves as functions of forcing period and constant mean zonal flow. Basically, Charney then looked for extratropical forcing of tropics to trigger convection in his mind that was needed, and he quickly realized that the penetration towards the equator depends on the background winds, and he figured out that easterlies make it harder for the Rossby waves to come down into the tropics, whereas westerlies and the associated Doppler shift, which we haven't got into the details here of the wave kinematics, but you can look up the tropical dynamics course, as I said. But it turns out that, as you see in this paper, there is a dependence on the forcing period, or the frequency of forcing, for the amplitude of the eastward propagating Kelvin waves or westward propagating Rossby and mixed Rossby gravity waves. So here the forcing period corresponds to westward propagation, i.e. absolute value of negative period. For the Rossby waves in the upper panel, westward mixed Rossby gravity waves in the middle panel, and corresponds to the eastward propagation of Kelvin waves here in the lower panel. The dashed curves are for the mean zonal flow of u equals 10 meter per second, so westerlies. The solid curve is for u equals 0, the background state is stationary, and the dotted curve is for easterly flow regime. And the forcing period is clearly showing that the Rossby wave amplitude is stronger for lower frequencies, and it's the other way for the Kelvin wave. So and they all depend on the background state. Okay, so the idea of which waves penetrate into the tropics depends on the forcing frequency as well as the background state. Obviously, amplitude corresponds to the amount of energy, and easterlies are typically associated with weak energies and westerlies with strong energies, but the forcing frequency is also important for this. So I'm going to leave it there. Obviously, in this introductory course, I don't want to get into too many details because we haven't covered all the background. But if you just remember that the theories of extratropical forcing of the tropics and the mechanisms depend on these ideas of how the waves are generated, the forcing frequencies, and what background flow regimes are. And we have only considered the zonal flow here, which is the most important one, because the Coriolis makes the zonal flows much more important than the meridional flows. Since the Coriolis changes with latitude, the constraint on meridional velocities is obviously much stronger than the zonal velocities, and the Doppler shifting of the waves generated is dependent on this background zonal flow. But as we said before, meridional flow, meridional shear and vertical shear also matter in terms of how the waves are Doppler shifted in wave number and phase speed, and where the energy gets accumulated, and so on and so forth. Okay.